that everyone attending might be a non-specialist. It's really aimed at non-specialist technicians. So maybe you do chemistry or biology normally, or that's your strong suit. But I'm going to go, as I say, right back to basics. And you can see here that I've got a board in front of me, and we've got some various different components. The components that I'm going to be using are from Bright Sparks for Kids. They're really good hardware and resources, and they're labeled, as you can see, and it does make things easier, especially for students that are just coming into electricity and circuits. So the first bit I'm going to start with is a series circuit. I'm going to do a series circuit, then a parallel circuit, and then we're going to start to incorporate multimeters. And then through the session, I'm going to do a section about all the different functions of a multimeter and how you might use them as a technician. Hopefully there'll be some tips in there that might help with your day-to-day job. So on my board, hopefully you can see nice and clearly, I've got 3 cells. And the first thing that I'm going to do is set them up as a battery. So when we connect cells together, we always put them in series. And across the top here, I've got a black terminal for a negative and a red terminal for a positive. And what we're going to do, I'm going to just wire these up now and talk you through it. And that will be the basis for what we're doing today. So one lead into the negative terminal here. And then I'm going to do a lead from the red positive terminal of the first cell to the negative terminal of the second cell, so positive to negative. And then from this positive terminal to the negative terminal of the third cell. And on this one, I'm going to put a red lead. So you notice that I put a black lead from the negative, and I'm going to put a red lead into this positive terminal of the third cell. Now, I know most people, especially the IOP, don't like coloured leads, or definitely don't like the black and red, but I think it's easier for people to understand and see what's going on with our circuit. So I'm going to connect our next bit onto our switch. So we're going to take a negative lead from the first cell to our single point switch here. And then I'm going to connect the lead from the positive terminal to this terminal of our bulb holder. So we've got a switch and 2 bulbs in our circuit. So like I say, we're going to do a simple series circuit to start with. So I connect from this terminal of the first bulb to that terminal of the second bulb, and now I'm going to connect the bulb to the switch. Now, at the moment, the circuit is open. The switch is open, so the circuit is not complete. Now, when we do circuits, it's important to sometimes visualize what's going on, and there's lots of different models. I quite like the rope model, and if you imagine that this is all solids and we've got electrons and they're side by side, there's no gaps between them, and the flow of current, or conventional flow of current, goes from positive round through the component, so through the filament of the bulbs, and then through the switch and back to the negative. So it's going round from positive to negative. That's conventional flow of current. We've wired our cells up, so now we have not got individual cells, now we have a battery. And because we've wired them in series, ideally, we've got 1.5 volts per cell. So 3 cells in series should give us an output of 4.5 volts. Okay.
Paul?
Yes.
Hi, sorry to interrupt. I'm Matthew, by the way, Matthew McKenzie. One of our technicians is sharing their screen. Chris, yes. I think it might be you. If you can just click on stop sharing, because we can see Chris's screen rather than you, Paul, at the moment.
Okay.
If he's not able to, it might be that I don't know what. Can you do it from your end, Paul?
Yeah, I've done it.
Oh, lovely. Thank you, Chris. Sorry, Paul.
Okay.
You carry on.
Right. Okay. Can everyone see me okay now? Yes? Right. So we've got our cells in series, so potentially, or ideally, we've got 4.5 volts from our now battery that we've wired up. And as I said, we've got conventional flow of current is from positive to negative. And as I said, it's quite good to try and have a model, a visual model of what's going on. And sometimes people use the rope method. So you have a joined piece of rope in a circuit and you move that through your hands and you imagine that it's passing through a component. So what you do, you'd close your hands and then you'd feel that rope going through your hands. And as you tighten it, as the resistance increases, you find that you've got heat and friction. And that's exactly what's going on through the filament of a bulb, for example. So now what I'm going to do, I'm going to close the switch and then hopefully you can see that my 2 bulbs have lit up. Okay, now a series circuit isn't used very often in real life scenarios, and I'm going to show you why. Probably the only one, and it's the one that most textbooks mention, is Christmas lights. But I'm going to undo one of the bulbs here. And I've closed the circuit and you can see that nothing's happening. So now we've created a gap in the circuit again because the bulb isn't connected properly and therefore the whole circuit doesn't work. And you can imagine that if you had that in lots of different real life scenarios, it wouldn't be a positive thing. For example, your car, if your heater went down, then suddenly you could find yourself without any headlights or indicators or windscreen wipers or anything else that functions within the car. So what we're going to do next is the parallel circuit. And this is the circuit that's mostly widely used in real life. So the circuitry in your home, again, that car example. So I'm going to switch the circuit off, open that switch, tighten the bulb up again. So I'll just make sure that it works. So they're working again. So now we're going to create a parallel circuit. So I'm going to disconnect those leads and we can go take this lead out from this bulb here. Move that bulb down on this one here. We connect this lead back to the switch. So I can switch that on, and now you can see that I have one bulb alight, and you can see that it's much brighter than it was before in that series circuit. And now all I need to do is wire these in parallel. So I'm going to connect the lead in here on top of that plug, and then into this terminal of our second bulb holder here. I'm going to put another lead into our second plug, and then into our second bulb holder. So now you can see that our circuit is wired in parallel. So if I close the switch, you can see that our bulb, or both our bulbs, are nice and bright. They're much brighter than they were in that series circuit. So going back to the real life scenario, the reasons why this parallel circuit is much more useful is if I undo this first bulb and then switch the circuit on, you can see that even though the bulb doesn't work at the top, the second one does. So again, I go back to that scenario in the car. You've got multiple different electronic circuits and components and devices in your car. You need to make sure that at any one time, if one goes wrong, it doesn't wipe out everything in your car. You can well imagine that, as I say, you're going down the road and maybe your radio goes wrong, but you can't then use the windscreen wipers or your indicators or your headlamps. So a parallel circuit is really, really useful. And the reason why that works is that now we've incorporated different branches. So each branch is almost its own series circuit. And the difference between the two circuits is that in a series circuit, the current remains the same. So the current remains the same wherever you measure it in a series circuit, but the voltage is different across the various components that you're using in the circuit. Whereas in a parallel circuit, it's the other way around. So the voltage remains the same, but your current changes depending on how many branches you have within a circuit. So that's our basics on a series and parallel circuit. What I was going to do next, I was going to try and show you a video of starting to incorporate multimeters in. So if we use a multimeter, we can use them as an ammeter and a voltmeter, so we can measure that current around the circuit, but we can also use one to measure the potential difference or voltage across each component. So there's a really big rule that when you're using an ammeter, you always put it in series in the circuit. And when you're using a voltmeter, you always put it in parallel to the component that you're testing. Okay, so let me try and see if I can share my screen with you, and let's start with a series circuit.
Hello, in this video we're going to look at using a voltmeter and ammeter in a series circuit. Here I'm just switching on the circuit just to check that it works, and you can see our bulbs will light up. We're going to use a multimeter and we're going to use the amps DC scale here and a 10 amp setting. So I'm going to turn the dial just to show you which way to point it to our 10 amp setting.
Paul, sorry to chip in. I'm not seeing the video here. I don't know about everyone else.
Marked COM.
Okay.
We're seeing your screen with the file list on there.
Let's try again.
Paul, we're not seeing the video.
Okay.
We're just getting a blurred version of your screen at the moment.
I don't know how we can sort that out then.
Is there a link for the video that you could share on the chat?
No, these are my own personal videos.
Well, and they're sitting on your machine, are they?
Yes.
So you should be able to share that application, really.
Yeah, I don't know why I can't. I'm in share. And I'm now playing.
You're not using multiple screens or anything.
No.
Oh, something's happening. If you just joined us, we're just having a couple of video problems for a minute. We're just trying to sort those out.
Can you see it now?
We can see a black screen. I'm just wondering whether it's a bandwidth issue.
I think it might be. Can you see any images yet?
We can hear some whispering, but not the actual video.
Right.
Yeah, perhaps you can paste the videos in the chat or send them to me, Paul, and I'll try from my end if you like.
Okay. I do apologise, everyone. For some reason, the videos are not playing at the moment. Right, what I'm going to do for the time being is that I'm going to try and do it manually. Can you see my screen properly now?
We can see you, but we can't. I don't think you're screen sharing at the moment.
No, but can you see me well enough if I show the multimeter now?
Yeah, we can see you quite clearly.
Yeah, right, okay. So here we have our multimeter. And you can see that we've got various different scales on it. And we're going to, the first one that I'm going to do is an ammeter. So we're going to use a lead in COM, and we're going to use a lead in the 10 amp socket here. So when you're using an ammeter, or you're using a multimeter as an ammeter, it's really important to often use the 10 amp socket, because if you use the milliamp socket, that's when the internal fuses of your multimeter can be blown. And that's when most multimeters that you'll have installed don't operate correctly. So if you use the 10 amp setting, that's when you've got a better internal fuse rating, so that they won't blow. The other thing is that the 10 amp scale is the one that you'd normally find for your digital ammeters. So what we'll do, we're going to go through to the 10 amps DC scale down here, and on my multimeter, the 10 amp setting is this one here. So if I click it round, that's the one that we're setting it at. And as I say, we're going to use this multimeter as an ammeter. So what I'm going to do, we've got the circuit set up as a parallel circuit at the moment. So I'm going to revert back to a series circuit. There we are. So now we're back to our series circuit. So the first thing to do, we're going to put our ammeter into the circuit, and I'm going to put this lead from the positive into the 10 amp socket, and then I'm going to put the COM socket. You'll always use a lead in the COM socket when you're using a multimeter circuit. that one is going to go into that terminal with the bulb. So the way that you want it to flow through, as I said before, as that conventional current flow. So your COM, which is normally a black lead, will be your negative lead. So if I switch this circuit on now, you can see that I have a 0.04 amps. If I put that on, you might be able to see it a bit better, hopefully. There you go. So that is our ammeter in our series circuit, and we could put that throughout the circuit and it should display that same value. Now we're going to use our second multimeter as a voltmeter. So we've got two different scales on this side of our multimeter. We've got volts DC and we've got volts AC. Now, you'd only tend to really use the AC one perhaps on transformers, but your DC you'd use in most circuits. And again, I'm going to use the same range that you would find with your conventional voltmeters at school. So that would be 20 volts. Most digital voltmeters have got a 0 to 20 volt range. Now on this time, again, like I said, we always put a lead into COM, and then we're going to put a lead into the volts, ohms, and milliamp socket. So you look for the socket with volts, ohms, and milliamps on. So if I switch that to 20 volts, and we're going to put our voltmeter in parallel to the component that we're testing. So I'll put the lead from COM up into this socket. So remember that our conventional flow of current goes from positive to negative. So our COM is our negative, so we want it towards the negative terminal of our battery here. And then I'm going to put a lead from that volts, ohms, and milliamp socket up onto the other bulb socket terminal here. So now we're wired up. Hopefully you can see that I have a voltage across that bulb of 1.97 volts. Now sometimes when you do this, you'll get a negative reading, and that's purely because the wires are the wrong way round. So the polarity is the wrong way round. And all you need to do is just swap the wires over. So if I do it with this one, and I switch the circuit off, and I put the red lead in there, and the COM lead, the black lead, towards the positive terminal of our battery, and then I switch the circuit on again, you'll see that I have a negative reading. Okay. So it's a very easy fix. Just swap the leads over, and that will be that. So now we're going to go into a parallel circuit. So I'm going to disconnect the leads. There we go. So we'll start off just by having our basic parallel circuit. There we go. Okay, so we switch it on just to make sure that it's working. Okay, so this time we can put our ammeter in between our two bulbs. So again, our ammeter, we're going to use our ammeter first. Our ammeter needs to be in series. So we'll put a lead in here, and then we'll put a lead from our terminal of our bulb into the volts, ohms, and milliamp socket, or even our 10 amp socket. So there we go. You can see, hopefully on this one, that we now have a reading of 0.05 amps. Now, if I had more bulbs on various different branches, the total current of the circuit would be divided between the bulbs. And what you would see is if we had a total current of 1 amp, you would see that if I put it into a third branch, you would see that it would be 0.33 amps. And then if I put the ammeter where it is now between the second and the first bulb, you would see that it would be 0.66 amps, and it would alter depending on where you put the ammeter. Now we can put our voltmeter across either one of our bulbs. So if I remember, we're going from the positive side really to the volts, ohms, and milliamp socket. And then we're going from COM to the negative. And we always put our voltmeter in parallel. Okay, so hopefully you can see here that I've got a reading of 3.226 volts. It's much easier to put the voltmeter across the components because literally you can, if I switch the circuit off, if we unplug that lead, move it up a little bit, and then connect it to that socket, now we will be in parallel to the first bulb. Now if I switch the circuit on, again we've roughly got the same reading, 3.27 now we're reading. So remember, in the parallel circuit the voltage reading should be the same, but the current is divided by however many branches you've got in your parallel circuit. Okay, so is there any questions in the chat? Let's have a look. Is everyone happy with the series and parallel circuit, and using the multimeter to be used as an ammeter and a voltmeter. Cool. Was it helpful? Has it helped anyone? Has made it a bit more clearer what you need to do?
Feel free to switch your audio on, folks, if you want to just respond.
Great. Well, yes, I'm getting some good positives, so thank you very much. I can see that hopefully that's made clearer. So what I've normally found that is that a series circuit is fine, but I've found that quite a lot of people get into difficulties when they're asked then to change that same series circuit into a parallel circuit, and especially when you start introducing ammeters and voltmeters into it. So hopefully you'll feel more confident in using those if you get asked to do either of those. Yeah, so that's the most common cause of the fuse, the internal fuses being blown, is that if you give the multimeters out, especially to lower school, they'll plug the leads into any socket, and then they'll whiz through the various different scales on the multimeter, and then eventually the internal fuse will blow. So and then you're very limited. You've got to take the multimeter apart, and you've got to replace the fuse. But I'm going to show you a bit later on. I'm going to go through some various different uses of the multimeter, and one of them is going to be a setup so that we can check a second multimeter to see if the internal fuse works or not. Okay, so I'm going to try again to share my screen, but this time I'm going to share a Word document, and I've got a bit of a test. So I'm going to give you, once I put it up on screen, I've got some various different components, and all right, hopefully you can see this. Can everyone see my screen?
We're just getting a black screen, Paul. I'm going to make you full host, Paul, and see if that makes any difference. Right.
Because it's saying to me your screen sharing is paused.
I have made you full host now, so you should have full. You had co-host before, but that should work.
Okay, so at the moment we can't see anything, no?
No, all we see is a black screen. But we do see you when you share your screen, so it's obviously working.
Can you see it now?
Yes.
Hey, we have a success at last. I think that that there might have been a problem. I might have optimized the video for sharing, and it might not have liked that. Okay. So everyone can see this document in front of you. So I have 15 components on it. So what I would like you to do, I'd like you to try and identify as many as you can. I'm going to give you some minutes to do it. And what I would like, either through chat, and you can take yourself off mute. I want to try and see who thinks that they can identify the most, and then we'll get you to run through it and see if you've got every single one of them right. So what I should have really now is some music to go behind it. I should have some nice countdown music, but I'm going to give you a few moments. And then, like I say, if in chat, you can let me know how many you've got. Okay, 5. We've got 5. 5 is our highest. So George, you can name all 15. Almost. Okay, so more than 10. So we've got 10 as our highest, apart from almost. And no cheating. I don't want any Googling or... 7. Okay, so 10 and almost is still our highest. I'm going to give you a couple more minutes. Go through one more cycle. 9. So 10 and almost is still our highest scores. Okay. Okay, so George, do you think that you have got more than 10? Yes. Okay, so George, would you like to unmute yourself? And then we'll slowly go through each component one by one.
Okay, can you hear me?
Yeah, I can hear you, George.
Actually, the number 2 is the voltmeter.
Okay, we'll start with number 1.
Number 1, I'm not sure. I think when I saw it, I thought it was the resistor that can took a lot of the rheometer. The rheometer.
Okay.
The rheostat. The rheostat.
Yeah. So no. So let
No,
me do that.
Because
so,
it's 10. Yes.
So number one is a thermistor.
I see. Mm-hmm.
Okay.
Yes, it changes by the temperature. Yes, yes. We have one.
Yeah.
Here. I didn't remember it.
Okay. So number 2.
Voltmeter
is a voltmeter. So that's what we were using our multimeter for earlier. Number 3.
It's a switch.
It is, but what type of switch?
It's actually it differentiates the circuit.
Yes, it does. It's a two-way switch.
Two-way switch.
Okay. So what is number? Okay.
Yes.
Have we got? Is everyone okay? So I've got a little comment in chat that what is number 1? It's a thermistor. Okay. So I'll go back to that because that's popped up in chat. So it's one of these, and I'll talk about that in a little while. We'll go through some of the components in a bit. So yes, so this is a two-way switch. So you can see here. So this is called a single pole or single throw double pole switch. So it's a single throw because it's just that, but it's a double pole. Where you've got a conventional switch, which is a single throw and a single pole. So quite a lot of times, these are used. These are asked for in A-level physics, and this is particularly good for a capacitor circuit. So you can do a charge and a discharge just literally by wiring it up to these two different terminals. So you were right, George, in that you can differentiate the circuit using the switch. Okay, so yeah, go on then, George.
Number 4 is light dependent resistor.
Yeah, so it's an LDR. It's a light dependent resistor.
5 is resistor.
Number 5 is a resistor. So here we've got a mounted resistor. So there you go. So the value of the, oh, hang on, what is 3? So bear with me, George. In chat, someone's asked what
Yeah, I saw it.
3 is.
I saw it.
So let's go back to the two-way switch. So number 3 is called a two-way switch. So we have what it would be called technically would be an SPDT, or DP, sorry, STDP, I'll get that right, single throw double pole switch. That's the one. Single throw double pole switch. Okay, so like I say, we'll go back. So that's the resistor. So this is number 5, and it doesn't matter what the value of the resistor is. You just use that same symbol. Okay, George. So number 6
is the ammeter.
Yeah, that's right. So that's
Number 7.
Number 7
is the diode.
Is a diode. So let me find one of those. There you go. So here is a diode. Now you can see, let me just recap on this. So you can see on here, it's the first component that I've shown that has a black negative terminal and a red positive terminal. That's because the diode operates only in one way. And you can see on the body of the diode, hopefully you can see that there's a silver tag on the body of the diode, and that always indicates the negative terminal. So you can see here that this is already mounted, and you can see that the silver tag is towards the black negative terminal. Yeah. Okay, yeah, well done, Alice. Thank you very much. So yeah, it's very, very important. So the diode only operate in one way, and when you're wiring it in, you always make sure that the tag end goes towards your negative terminal. Okay, so number 8.
It's a cell.
No, it's not. I'm going to be picky now. Alice has got it right. It's a battery.
Yes, yes. I wanted to say battery, but yes, okay.
Yeah, so I'll show here. So here's an individual cell. So you can see that we have that long line with the positive and the shorter contact with the negative. But when we put them together, as I did on the board, once you put two cells together, or 3, and you wire them in series, they then become a battery. Yeah, battery is multiple cells. Exactly right.
9 is a bulb.
So 9, yeah, 9 is a bulb that we've got up on the board.
10 is a rheostat.
Yes, so it's a rheostat or a variable resistor. So here we've got the variable resistor here. Okay, number 11.
It's a solar cell.
It is a photovoltaic cell. So that's that here. Very good.
12 is a single switch.
No. Does anyone know what 12 is? Anyone on chat can tell me what number 12 is? It is a form of switch, but it's a special kind of switch. Has anyone got any idea on the chat what number 12 is? Not a closed switch, not a transistor, no. Okay. Are you ready? Okay, so it is a reed switch. Okay, we've got on here listed on this that it's a magnetic switch. It's because you need a magnet to operate it. But a reed switch, I don't know if you can see here, is within a glass cylinder, and there are the contacts inside, but they're normally at their normal point, they're just ever so slightly apart. They're ever so slightly open. And what you need to have is you need to have a magnet across it, and then that will close the contacts, and then that will let your circuit operate. So yes, so number 12 is a reed switch. So yeah, that's exactly right. REED. Thank you very much, Alice. That's great. These would be probably most likely used in an alarm system, to be honest. Get a lot of reed switches in alarm systems.
So number 13, I think it's a capacitor.
It is a capacitor. That is right. So let me find one of those. Here we go. Okay, so here is your capacitor. And again, you can see that we've got our black negative terminal and we've got our red positive terminal. If you look on the body of the capacitor, you'll see that it's marked again, and you'll see that it's only down the side towards the for the negative terminal. So you know that your negative arm of your capacitor is towards your negative terminal. So I've got a different one here just to show you an example. This one very nicely has got arrows on it as well as negative symbols. So it makes it very clear which end of your capacitor is your negative terminal. It's really, really important when you're using capacitors that you use them and you wire them up correctly. Otherwise, you can cause them to burn out, or in worst case scenario, explode. So it's really important that you make sure that you wire your capacitors in the right way around, the right polarity. Okay, number 14.
It's an LED.
It is an LED. Okay, so here's one of those. Okay, so again, so it's a light emitting diode. Thank you very much, Alice. Yeah, a light emitting diode. And you can see again here that we've got a negative terminal and a red positive terminal. Because it is a diode, it only operates in one direction. Let me just have a look and see if I've got one loose, and I can show you. So you can see that on a loose LED component, hopefully you can see that one leg is slightly longer than the other. Okay, and then that allows you to work out which way round your LED should be connected. Number 15.
When it comes to 15, I don't have any idea.
Okay, so straight away Chris is on it. Straight in there, Chris. So here we go. It's a push button switch.
We have some of this, but I didn't know that this is the symbol.
Yeah. So you literally physically have to make the switch close, and then it should spring back up again. So you're closing the contact of the switch with your finger.
Mm-hmm.
A lot of schools that with older kit, sometimes you have just a piece of metal up above and a little black plastic stopper on top, and then you have to physically push the metal switch down, but then as soon as you take your finger off, it'll come back up. So there we go. So yeah, that was an excellent run there, George. Thank you very much, and thank you very much to you, Alice, for typing that up for everyone. We had a very good run through the various different 15 components. Okay, I'm going to stop sharing. The next thing I'm going to do is we're going to look at some circuits. So if I close that, I do apologize, my computer is lagging a bit. There we go. So hopefully everyone can see that. And what I'd like you to do is to take a few moments to have a look at those two circuits, and then in the chat, or just let me know why they won't work. Can no one see the?
Yeah, we can't see the circuit again, Paul.
Okay. Again. Can you see it now?
No, it looks like it's loading or something at the top. I don't know whether it's downloaded locally.
Before sharing it, that'll make it easy to, rather than going through your computer, open the file first on your computer before sharing it.
Yeah, I think that's probably the issue.
I had already opened them.
Can you drag the file to the chat so that people can open it for themselves?
Right. Can you now?
Yes.
You can see that now. It's good to go.
Right. Okay. Okay, in the chat, would someone like to say why the first one, the top one, isn't working? Yeah, George, you can answer on chat. You can unmute yourself, George, if you'd like to say.
Actually, they have the opposite polarity. I mean, the LED needs to be connected in the opposite way.
Exactly right. Okay, so remember that we had our light emitting diode. We've got our positive and negative terminals, and as I said, it is a diode, so it will only operate in the right polarity, the right direction. And so, as you can see, the negative terminal, if you follow the circuit round back to the battery, you'll see that the negative terminal is towards the positive terminal. So we need to make sure that that's the other way round. So yeah, George, that's right. What about the second one? Yeah, the button does need to be pushed, but there's something else again. Okay, so yeah, it's the, okay. The lower symbol is a buzzer. Okay. So yeah, the push switch has to be depressed for the circuit to work. But then there's something else that's wrong. That's right, George. So yeah, so again, our buzzer only works with the correct polarity. So we've got our negative and positive terminals again. And so you can see that again, if you follow the circuit back round, so if you take, for example, the positive terminal on the buzzer component symbol, and you follow it back round the circuit, you'll see that it's towards the negative terminal of the battery. So we need to make sure that the buzzer's reversed. So it's the correct polarity, and then we need to make sure that the switch is closed. I'm going to try it again. And then I'm going to share one more. Let's try. Okay, can everyone see that?
No, it's not come up again.
Okay. Right. I shall try one more time. Here we go.
Yeah.
Okay, so now we have our circuit. If you can have a look and let me know what is wrong with this circuit. Okay, yeah, so Alice, that's right. Up at the top top left, as you look at it, there is a break in the wire. And yes, we have an open switch. So can you tell me what switch that is again? We've done it on our it is a reed switch, Alice. That's right, and Chris. Yeah, it's a reed switch. So as I said before, if I show you it again, so its natural state is as an open switch. So the contacts are just apart, and you need to have a magnet across them to close that switch up. So yeah, so a break in the wire, and then you need you need to close that reed switch for that circuit to work. Okay. So I'm going to stop sharing now. Now, what I was going to do next is I was going to go through the multimeter and go through some uses. We've got about 3/4 of an hour left. So what I'm going to do, I'm going to go through the multimeter here that I've got, and the various different scales, and then some uses that hopefully you'll be able to use day to day when you're at work. So we've already used the volt scale here. So this is the volts DC range, and you can see here that we've got millivolts. We've got 200 millivolts, 2000 millivolts, and then we've got 20 volts, 200, and 250. So that is our volts DC range. And as I said before, that would be the one that you'd use. The 20 volts scale or range would be the one that you'd use as a voltmeter. Then the next one down, you'll see here, hopefully, you can see that we've got a volt and then a wavy line. So our wavy line denotes that it's an AC range, and they're pretty big. So you've got 200 and 250 on there. And like I say, the most times that I've used those would be with a transformer or the National Grid demo, for example. Then the next one down is really quite useful. So hopefully you can see that. It looks like a diode, and then this one's also got some sound bars. Sometimes it has a musical note, but this is really useful. This is a setting for testing continuity. Okay, and that's really handy. We're gonna start off with that when we move on from me going around the range. The next one on here is a square wave output, and this is almost like a test signal. So you could put that into an oscilloscope, and then you'd get a square wave output. It's normally used for testing things like amplifiers, just to have a test signal to put through it. Then we're going round. The next bit is around here is the amps DC range. Okay, so you have a 10 amp setting that we were using before, and then we have our milliamps and then microamps. Okay, and then the next range round on the other side to our volts scales are our ohms. So this is our ohm scale, and it's in a range, it's called a decade. So it goes up in multiples of 10. So we start off with 200 ohms, then 2000 ohms, and then up to 20,000 ohms, and then 200,000 ohms, and then 20 mega ohms, and then 200 mega ohms. Now, again, that's a really useful part on our multimeter, and I'll show you that now. So the first thing I want to go back to is this testing continuity. Okay, so with our leads, when we're testing the leads, this is by far the easiest way of testing your leads, and you can go through them really, really quickly. So let me bring it a bit closer to the camera. You are going to use one end of the lead into COM, and then one end of the lead into the volts, ohms, and milliamp socket. And then you're going to switch it round, and you get this annoying tone. So if it's got an inbuilt speaker, you'll get a tone to say that the circuit is complete, but that's not all that matters, to be honest. It's the reading as well. So you can see here that I've got a reading of 000. Okay, what I always do when I test my leads is I give them a wibble. So you give them a wiggle on the lead, and that will test to see if there's any breakdown in the core of the wire itself. So these are like multi-core wires that make up the leads. And sometimes when they're a bit older and they've had a bit of abuse, they'll start to break down. So those strands inside start to break, and so you start getting high resistance. The other thing is most students, and dare I say teachers, don't hold the plug when they're pulling the lead out of components, and so you put stress on that joint. So either the joint goes, or you start stretching the various different strands of copper wire inside that make up the lead. And so what you do, because these are nice shiny new leads that I've got here, what I would be looking for is if I started to move this around, let me give it a wiggle, if I start to see the reading fluctuate, and perhaps anything over 0.05 or 7, I'd probably go for 5 as my top figure, to be honest. If it starts fluctuating up and down, then you know that you've got a breakdown in your lead somewhere. The other thing is, if you plug your lead in and you don't get this noise, and you go either, it depends on your multimeter, it'll either show a 1 or it will show OL, over limit. That means that your lead's dead to start with. So your lead won't work at all, and it's not conductive. So there's no continuity in your lead to start with. So that's the quickest way to test your leads, and you can fly through those. So is that helpful to people already? Does everyone do that with their leads and test them like this already? Let me know on the chat. What else? So you can also test your resistors. Normally in a technician, especially if it's legacy, so pretty much every prep room that I've taken over, there's either a component tray or more often than not, a Grapnels tray full of random resistors that they're just scattered. So they're all mixed values and they haven't been segregated. And it's a really good task to do. And once you get into the swing of it, it doesn't take long to sort them out. So on your resistor, you can see that we do have our color code. So there is a color code system to identify the resistor. But there's a couple of things wrong with that. And I think there's more to life than knowing the color code of resistors off by heart. I know some people do, and I've worked with someone who can identify all the color codes and know them off by heart. But there's a problem with that, and that's how good the paint is on the resistor for a start. So sometimes even brand new resistors, the paint bar, the band, is really poor, and it's hard to distinguish what color that band is supposed to be. And there's another important thing, is that, yeah, you could look at it and you could say this is a 1 kilo ohm resistor, but you don't know if it works or not. So it might look okay outside, it might not look burnt out, but if you put it across a multimeter, then not only do you get to know that your resistor is working, but you also know what the value is. And what I found is that most times resistors are bought in quite large batches of value. And so as you go through the tray, you'll start to recognize certain different values, and then it becomes even easier then to segregate them. So how do we do that? We're going to use the ohm scale on our multimeter, and it doesn't matter which lead you plug in. So one lead always goes into COM, and it doesn't matter which way round, what terminal on your resistor you use. Obviously I've got these ones mounted, but normally, I'm going to show you in a minute, you put a couple of crop clips on the end of your lead and connect it to multimeter. This time we're going to put the other lead into the socket marked volts, ohms and milliamps. Now, because the resistor hasn't got any voltage, we're not putting any input into the multimeter. Now, rule of thumb is that you should go down the scales on a multimeter. So if you're measuring a voltage, the good practice is to start from the highest scale and work your way down. And that's why, as you can see on this multimeter, even switching it on, the only way that you can go is from going down the scales, or the value of the scales. Because the reason being that if you've got a really high voltage coming into the multimeter, you could potentially damage it by using one of the lower indicator scales. So on this, it doesn't matter because we're not putting an input current or voltage into the multimeter. So what we can do, we can start right at the bottom of our ohm scale. So we can use our 200 ohm scale here. Now, this is something that I was saying earlier. So it's going to tell you one of two things. First of all, is your resistor working? Well, at the moment, that could possibly be no. The second is it larger than 200 ohms? The scale that we've got it set on at the moment is 0 to 200 ohms. So I know one of two things. either this resistor isn't working or it's larger than 200 ohms. Forget the fact that it's labeled, and we all know that it is larger than 200 ohms, but that's the thing that we're looking for. So then what you'd do is then you'd click it up to the next scale. So now you can see that we do have a reading. So that tells me, one, the good news that my resistor is working. It also tells me that I've got a value of 983 ohms. Well, they don't make a 983 ohm resistor. So now this is where it's quite handy to perhaps look in a catalogue. So when you're doing this, have the catalogue open on the page of resistors. So, you know, whatever company you use, whether it's Timstar or Brecklands or SLS, open it up onto the resistor page, and then you'll see all the various different values of a resistor available. Now, there's something to bear in mind, that there's always a tolerance built into a resistor. So we know that this is a 1 kilo ohm resistor, and that is the tolerance within it. So we won't get 1,000 necessarily. The higher up you go, the higher the reading will be off from what it's saying. So if I used a 10 ohm resistor, let me see if I can find one of those, and I'll show you that. So let me switch that off. So I've got two. I've got one that's mounted, and then I've got this one here. So I've got one 10 ohm resistor that's mounted already. And then I've got this one here. So this one is a ceramic resistor. So it's rated at 10 ohms. Now on here, hopefully you can see that. So it says 10 RJ. So on lower value resistors, they often come in as R. So this one says it as well. So 10R. And it's when you go up in the range that they'll start showing kilo ohm or mega ohm. But for 10s, quite often the labeling will say 10R, or maybe it's you know, a 2.2 R. The packaging will say that, will show an R rather than an ohm symbol. So don't be put off by that. I think that's what I'm trying to get at. So if you see an R, it's basically the equivalent of a ohm symbol. So what we'll do, we'll connect up this 10 ohm resistor first. Again, we'll put it on the 200 ohm scale, and then hopefully, there you go, you can see. I'll put the backlight on. You can see that we've got 9.8 ohms. So sometimes you'll have 9.9, but sometimes it will be 9.8, and that will let you know that it's the 10 ohm resistor. So let's try with this ceramic one and see what we get. So if I unplug, I'm just going to unplug that one, and then I'm going to get some crop clips, because we need to crop clip that together. So I'm going to put two crop clips on the ends, and again, it doesn't matter which way round you're hooking it up. There we go. So we go back round to the 200 ohm. And there we go. So this one is flicking between the two. So it's steadied at 9.9 ohms. Okay, so it's a 10 ohm resistor. It's a 1% tolerance on it. And so you'll know that when you see that, you know that you've got a 10 ohm resistor. And like I say, when you start going through your random tray of resistors, you'll start to see the same values, because they'll come in packs of 100 or 50 at least, and so you'll have multiples of the same thing. So various different resistors. There's another one as well. So we mentioned one before. So our variable resistor. So this is a rheostat. For anyone that's not au fait with those, so it can be a fixed resistor. So these two terminals here, if you put your leads in to those, then it uses the maximum width of the resistor, and that will give you your fixed maximum value. But to use the variable slider, you connect one lead into the top here, and then the other lead into the bottom here, and then you've got your slider that operates across the top. And I can show you that, I can demonstrate that with our multimeter again, nice and simply. So on here, on my rheostat, it's listed as 55 ohms. So let's see, I'm going to do the fixed. So I'm going to put the leads, I put the leads in to both these bottom terminals. So that is our fixed position. And then if I go back round to 200 ohms, what have we got? So we have got 53.2 ohms. Okay, so now if I disconnect, let me show you. If I disconnect one of the bottom terminals and I put it into the top for the slider, so now we've got one lead going into the slider and one lead onto the bottom fixed terminal, I should be able to display that decrease. So this way towards this upper terminal, the actual resistance is increasing. I don't know if you can see that. If I finish sliding that across the top, you can see that the resistance is increasing. Okay, so if you remember that when the slider is closest to your top terminal, that's maximum resistance. Okay, and then if I slide it back down the other way, there you go. So now we've got no resistance whatsoever. So 0 ohm resistor. So again, it's a good way of checking, and a quick way of checking, one, that your rheostat is working, two, what your actual value of the rheostat is, or your variable resistor, and then knowing which end is the maximum resistance, which one is your 0. Okay, we can also show, just while we're on it, if I switch the multimeter off, I can show you on the variable resistor on this one. So it's basically a potentiometer we've got here. We've got a dial that we're turning. Exactly. Well, there you go. So that's right. So yeah, pupils often get that wrong, and it's good to show them. It's good to show them how that operates, because there's multiple terminal sockets on them. They'll plug it into anything just to see what happens, or see if they can make a difference in their circuit. So quite often it's a bit of a distraction. So if I plug a variable resistor in, whoops, I switch our multimeter back onto 200 ohms again, and I'll put the backlight on again, so it makes it a bit easier to see. See if I can bring it up so you can see it here. There you go. So that's on maximum, and then as I bring it back round, we're on 0 much. So what are we getting out of here? 96 ohms. So potentially this would be, although it's showing 96 ohms, potentially this would be 100 ohm variable resistor. Okay. Now, what else can I show you? So remember, we talked about the capacitor. You can also check your capacitor is still working. So sometimes they do get burnt out, and it's good to check those. Is a really quick and easy way of checking them. So what we'll do, I'll show you it on this one. You put a lead into a negative terminal, and that can go into COM on the multimeter. So you have your multimeter, you remember you have that COM socket. So as I said before, negative lead should go into the COM socket, and then we'll put a lead into the positive terminal, and we're going to put it into the volts, ohms, and milliamps socket. So it's going to go in on this multimeter, it's going to go into this middle socket here. And what you can do is you can flick the multimeter over to the 2000 ohm socket, and you'll get that symbol there, that over limit. And what you want to do, that reading's fine. You want to leave that for a few seconds. So basically what we're doing is that we're charging our capacitor from the battery within the multimeter. And what you can do, you can see if it will hold the charge, because as soon as you flick it over, which is what we're going to do, we're going to flick it over to the 20 volt scale so that we can get a reading. And as soon as you flick that over, if our capacitor was broken, you wouldn't get any stored charge. And the other thing would be that it would discharge straight away. So let's see, I've had that on for a few seconds, as you've seen. If I put the multimeter over to the 20 volt, you can see here that we've now got 1.18 volts stored on our capacitor. So it's a very quick way just to check that your capacitors are still working. And remember what I said earlier about making sure that the polarity is correct and the markings on the capacitor. I've got another one here. Let me switch that on. I've got a, this is called a little super capacitor. You can see that it's a little flat disc. This one, that one's more like the conventional ones you've got. And you'll see that it's got on there a rating of farad. So that's the capacity of charge that the capacitor has. And then it's rated up to, this one is rated up to 63 volts. So this one's quite high. So when you look at your capacitors, and this is another thing to be wary of if you ever give them out to, say, GCSE students, is that they've got a voltage rating on them. So this one, for example, is rated at 5.5 volts. So really what you shouldn't do is go exceed that, or try to exceed it. Yeah, so that's right, George. Sorry, I didn't see that in the chat, but yeah, you can have fun alternating the intensity of light, or varying the intensity of light with an LDR. I was going to come on to that. So for the characteristics of various different components on the multimeter. So if I go back to this capacitor, we know that it's 63 volts, so that's fine. So again, I'll put the positive lead into this, or the red lead into this positive terminal of a capacitor, and that's going to go into the volts, ohms, and milliamp socket. And then I'm going to put the black lead, just so it's easier to see, in the negative terminal, and that's going into our COM socket. So again, hook it over to 2000 ohms, leave it for some seconds to do its thing. So we're gradually charging up this capacitor using the internal battery on our multimeter. And then if we go to 20 volts, I haven't given it enough time because this is a much bigger capacitor. It's going to need a bit more time to charge it up. What I can show you in the meantime, we can have a look at a thermistor, and then because you mentioned it, George, we can have a look at an LDR, and we can show the characteristics of the component by connecting them to our multimeter. Let's just see. I'm just interested to see if we've got. There you go. So we've managed to charge our capacitor sort of just shy of 0.6 volts. So like I say, it's a good way, another way of using your multimeter to test components. So let's have a look at our LDR. So our LDR, again, it doesn't matter which way round we connect it. So you can put that in whichever way you like. And this is going to have quite a high resistance. So if I have it on 200 ohms, it's too high. But if I move it, you'll see that the darker it gets, the higher the resistance. Okay. But if I take so I've got my finger on the LDR at the moment, and you can see that I'm over limit. So, and that's on 2000 ohms. If I go on to 20,000 ohms, now you can see that we're at 4,000, so 4,500 ohms. That's what that will show, because we're starting from 2000 ohms. So our, in this range, our 0 point is 2000 ohms. It's actually getting higher. We're nearly at 6,000 ohms. But then if I let it into the light, you'll see that the resistance is decreasing. So now we're at 987, or depends where I orientate the. So if I point them up towards my lights, we've got about 500 ohms there. If I point it towards the window behind me, we're about 386 ohms. So actually, for a STEM club or a science club, that would be quite a good investigation. You could do all kinds of different things with that. You could, it's the same with using a solar cell. You could have various different light sources on it, mask it up so that it's reducing the amount of available light coming to it. So very simple, but it's something that the students actually would find quite, would find quite interesting, because it's something that they wouldn't do in class with the normal curriculum. And then it helps with their understanding about how these components actually work. And you can link it with this thermistor. So with this light dependent resistor, you notice that the darker it got, the higher the resistance. Well, this works as you either get NTC, negative temperature coefficient thermistors, or you get positive temperature coefficient thermistors. So with a negative temperature coefficient, you'll notice that the lower the temperature, let's see if I can show you. So at the moment it's over limit. So again, we're about 6,300 ohms. But if I put my finger on it and I heat it up, you'll see that gradually that resistance is decreasing. Yeah, it is inversely proportional. So yes, so what happens is, and the simplest way that I put it and the way that I'd explain it, maybe if you didn't want, if you weren't going to that terminology, is that remember that when you've got say the sunshine for the LDR, the resistance goes down. Well, in the sunshine, you'd have higher temperature. So with the higher temperature, the resistance goes down as well with the thermistor. So they work along the same ways. So if it became dark and colder at nighttime, the resistance would increase. Okay, so this one is called a negative temperature coefficient. Okay, so there we've got some examples of where you can use your multimeter to show the characteristics. Yeah, and some schools have got the function to measure capacitance, but I just want to keep it simple. I want to keep it simple at the moment, so that we're just going through some simple circuitry with our multimeter, so we can show some basic characteristics of our various different components. Now, one other thing, I noticed that we're coming towards the end of our time. Testing the internal fuse of your multimeter. Well, if you get two multimeters, one you're going to put on testing continuity, and one you're going to put on your milliamp scale. Okay, so testing continuity, this one, black lead, one lead in COM, then one lead in the volts, ohms, and milliamp socket. So you're going to set up both multimeters the same. Now we're going to connect the lead from the COM into the COM socket of the second multimeter. Yeah. And then we're going to connect the lead from the volts, ohms, and milliamp socket to the volts, ohms and milliamp socket on the second multimeter. On this one, you're going to test the continuity. So we put that down there. Now, at the moment, you can see and hear nothing. So our second multimeter isn't switched on. But what I'm going to do, I'm going to put it onto our milliamp range. Straight away, you can hear that tone, and also you can see that there is a resistance. So I've got a slight resistance on our continuity, and I've got a slight resistance readout from our second multimeter. That is telling me that the fuse is good in our second multimeter. Yeah. So that's a really quick way that you can test a second multimeter to see if the internal fuse is good or not. Because quite often a teacher will come in and they'll say, I think the fuses are blown, but apart from you unscrewing it, which can be a bit time consuming, especially if it's needed quickly to go back into the lesson, you can positively identify whether the fuse is blown or not. So that can be really useful. And what I would suggest as well is replacing the quick blow fuse, and you can get a temperature reset ceramic fuse, and you can put those into your multimeters, and that without damaging the circuitry inside, that will stop you having to replace them time and time again. So that's quite a little tip. I've got another, I'm thinking, so we've got a few minutes just before I go to any questions. I've got a nice little thing that I like to show with a multimeter as a bit of an investigation. So this is a nice one, either for open evenings or as, again, a science club or STEM club investigation for the students. You can show that that we can be electrolytic cells. And you can connect our electrodes here. These are going to be our electrodes. And we've got copper and zinc. So we're going to put one lead into COM and one lead into the volts, ohms and milliamp socket. And then what you can do, you just connect them up. It doesn't matter which way round, but you connect them up onto the big crop clip that you put onto your electrode. There we go. And then what you can do, you just put it onto that 20-volt scale again. Oh, now you can see, hopefully you can see that I've got a negative reading. So just by me holding both of these, you can see that I'm putting out nearly 0.7 volts. And what you can do, you can investigate putting your palms on there. And normally what I do, I like to do this as a face-to-face activity when we're doing the proper face-to-face workshops and get everyone to have a go. And the classic that I've had in the past is that I had a gentleman that was about 6'5", huge, broad rugby player. And he stood at the back, letting everyone else go first, because he thought that his big poor hands would give out the highest voltage. And then he was absolutely ashamed that he wasn't, and it was in fact the 5'2" lady that had managed to produce the highest voltage output. And you can try just by showing by holding one finger how much the voltage drops, get higher contact area and the voltage increases, and then you can try with different electrode materials. So you could use aluminium and vary them up just as a really simple investigation. Well, there you go, everyone. It's 1 minute to go. I hope you found it useful. I'm sorry about the videos, but what I can do, we can make sure that you can access those. But I hope that you found it really useful. If you have any questions after the session, or you think that I might be of help, then you can always get in touch with me. We can make sure that you get my contact details, and yeah, it's possible that I can even come, if you like it, I can do on-site visits as well, and I can help with any non-specialist technicians that you might think that I could give you a bit of a hand in the prep room. Yeah, we're making sure that the recording's available. The only thing that I'm asking is that we make sure that it's only for Harris Academy technicians. So please don't just share it generally with any technicians that you might know outside of the Harris Academy network.
Thanks very much for that, Paul. Great session there, and despite the challenges, I thought it was very informative. Thank you very much. I certainly learned a few things about multimeters I didn't know. So thanks for coping with all the challenges there with the equipment. It's very stressful when you're in that position. Thanks, everybody. I've put a little link to our evaluation. I'd be grateful if you could fill that out so we get some feedback on the session, and if there's any questions, please do stay behind and we'll try to answer them. But thank you very much, and hopefully we'll see you again soon.
Thank you very much, everyone. I hope you have a really good rest of the day.